Right, so let's start. So last time I started to explain how can you calculate the power in efficient circuits. Okay, the previous chapter was about how can you calculate the voltage, current, how can you calculate the total impedance, and this was a question in the exam. This chapter is going to focus on power. As I told you also last time, there is a big difference between DC circuits and AC circuits. In case of DC circuit means the sources you have are actually DC. So in DC circuits, so the voltage is actually constant, as you see here. It does not, it's constant value. Simply the current. That's why the power is constant all the time. It's constant. This is in case of DC circuit. And the way you calculate the power here, as you see, if it is false, you have only one way to calculate it. V is equal V times I. If it is a resistance, you can calculate the power into the resistance by three different ways. Okay, which is V times I. V is the voltage drop across the resistance times I, or it can be I squared R, or it can be V squared divided by R. The three ways gives you the same result. Also here, we explain the power conservation, okay, which means the amount of power generated by the sources should equal to the amount of power consumed by the resistance. Okay, we are going to have the same thing here in AC circuit. In AC circuit, you should understand the situation is different. So, in case of AC circuits, the situation is different. Why? Because the voltage is not constant. It's going to change over the time. Same thing for current. That's why we don't have, that's why we are going to talk about what we call instantaneous power. So the power at each point, at each time, because the power changes, right? Why? Because the voltage changes and also the current changes. It's the same thing here. You can see the power should equal V times I. Okay. And as I told you, if we do the calculation V times I and you do some algebra manipulation, we found that the power has two components, two parts. This one here, it has a positive power all the time this way. Also, it has this power as well. Okay. So again, what I did, I just multiplied V by I. V is sinusoidal voltage. I is sinusoidal current. I just multiplied them together, and then I did some mathematical manipulation. I found that this is the power. Okay, we have two components, so this should equal two components. This component plus this component. Okay, this component actually we call it P, or the average value for this component, if you take the average value, should equal to V times I. V here, V, this is the magnitude of V in the complex domain. I cosine theta minus theta I. So this should give you the average value you have here. This is average value, okay? Where V here is actually V maximum divided by square root, and the I is actually I maximum divided by square root. In that book, you will find the same formula, but actually it's divided by 2. What? What? But in the textbook, the way we calculate the magnitude of V, it's actually only V maximum. R is actually only V maximum. That's why they are the same. Here, when we calculate V, we V maximum divided by square root of 2. Okay? And this component here, we call it active power. This component, okay? And this is the average of active power. And but if you look at the second component we have here, you can see this power. It is positive for some time, it is negative for some time. Okay. And if you want to get the maximum power here, the maximum power equal V times I sine theta V minus theta I. So this is actually the big value, the maximum value here. Okay? And this part, this one we call it Q. We name it Q. And this kind of power, we call it reactive power. Reactive power. Okay. So you can see the difference between these two kinds of power is this one all the time it is positive. Okay. Which means we actually, if you have a source and we have here an impedance, positive power means you are gonna transfer power from the source to the impedance. Is that okay? That's why it's positive. But for the second one here, for the reactive power, actually in the positive part, you transfer power from the source to the load. In the negative part, you actually transfer power from the load to the source. You got what I'm saying? Yeah. And but how the source can actually send power to the source? Simply because the load actually in this case it should have an inductor or a resistance. Sorry, inductor or capacitor, because these two elements are storing power. Storing power. They store power and then you release power. That's how it is. Also, last time I told you. Remember P and Q, okay? Because we are going to use it shortly. One of the things is also I said last time, this power is actually bad power. We wish if we can get rid of it completely, because this power is not going to be consumed by the load. This power is going to increase the losses because you take power and you lose. Okay, there are some loss, and then you send the power, there is loss. Okay? By the way, the average power here is zero. The average power is zero. Okay? And as you will see in details when I go to the slides, if you have a resistance, in case of a resistance, you have only active powers. If the load is resistive, you have only active power. However, if the load is inductor or capacitor, you have only reactive power. That's okay? You have only reactive power. One of the things also I told you last time here, how can we so again, what we want to do, I want to maximize P and I want to minimize Q, because this is a bad power. How can you do that? You can see what is common between them is actually this angle here. Theta V minus theta I. Theta V is the angle of the voltage. Theta I is the angle of the current. Same thing here. Imagine if you can make theta V minus theta I equal to 0. Okay? Cosine 0 is 1. So by this way, I can maximize this power, because the maximum power I can get here for P is when this cosine is 1. This is a maximum value for cosine, right? And here, this will be 0. What I'm saying? That's why we do our best. We try to make theta V minus theta I as close to 0 as possible. Okay? And there is a way to measure it, how close you are to 0. Okay? That's what we call power factor. So there is something we call it power factor, PF. Actually, this one measured cosine theta V minus theta I. Okay? So the best value I can get for power factor is 1. This is when theta V minus theta I equal to 0, because cosine 0 is 1. Okay? So we are trying to make the power factor as close to 1 as possible. If it is 1, so actually we are gonna maximize P and minimize Q, or actually Q 0 in this case, if you can make it 1. Okay? That's why, as you will see, there is something we call it power factor correction, which means if the power factor is far from 1, I need to add some elements to the load to make the power factor correct the power factor to make it close to 1. Okay? So for example, you will see in one example, for example, if the load is inductor this way, okay, maybe I will find that power factor is very small, which is bad. So maybe I'm gonna add an inductor this way so that when I calculate the total load, I find the power factor is close to 1. I will give you more details about this one, okay? But let me continue. So there are more details on this one. So here, so now P is actually the magnitude of V times the magnitude of I cosine theta V minus theta I. P, I would say Q, this one Q. So Q here means the maximum value here. Q is actually V times I sine theta V minus theta I. Is that okay? So now the question is that, how can you calculate the power? Okay, similar to before. If you have a circuit in the time domain, you need to convert the circuit to the complex domain as we did before. Is that okay? The only difference is when you do this conversion, there is a small difference when you have V maximum cosine omega theta plus I. When you do this conversion, so V maximum here, it has to be V maximum divided by square root of 2. Okay? So when you convert, instead of making it V maximum, you need to divide by square root of 2. Okay, so I will so that you can use the formula. I will explain. Okay, if you want to make it V maximum, it's still okay, but you need to change the formula. Okay? But anyway, so after that, what you have to calculate, you need to calculate what we call complex power. Complex power is actually the power in the complex domain. Is that okay? I will tell you how. But after you, the surprise now, after you calculate the complex power, you will find the complex power is actually P plus JQ. Is that the same P we have here? The answer is yes. So you find the same P, which is this one here, is the first part. The second part is actually this one, which is J, the imaginary part. Is that okay? So what I'm saying in the complex domain, after you calculate the complex power, I'm going to tell you how. I didn't tell you how yet, but there is a formula to do that. After you calculate the complex power, you will find the imaginary number you will get, the complex number you will get, the real part here is actually, imagine this part here, imaginary number here is actually Q, which means whatever you get here in the complex domain, this is actually the average of the active power, because this one is the average of the active power. But this one here, Q, this one actually is the peak value, the peak of reactive power. Is that okay, guys? Now I will explain to you how can you calculate the complex power. But what I'm saying is, after you calculate the complex power, you are going to have two parameters, V and Q. And you already know V and you already know what is Q. Is that one more important thing? If the load only resistance, you are going to have only B. You are not going to have imaginary bar. If the load is only inductor or capacitor, as you will see, you will have an imaginary bar, but you are not going to have a real bar. Make sense? For sure, if the load
Yes. Combination.
resistance and then capacitor and inductor, series or parallel or whatever, you know you are going to have both of them. Make sense? Now I will explain how can you calculate the power in the complex domain. So number one, if you have a source, either it is current source or voltage source, the formula you can use for the complex power F should equal V times I asterisk. Okay, what is asterisk? This is the conjugate. Conjugate means, for example, if I equal 2 plus G3. Okay, so I asterisk should be equal to 2 minus G3. So the imaginary part, you have to, if it is positive, you make it negative, you have to make it positive. And if this one is angle, so if I equal to 3 with angle 20, so I asterisk the conjugate of I is going to be 3 with angle negative 3. Make sense? So here it has to be V, I asterisk. Okay? And I explain how can you calculate the conjugate here. Either the imaginary part here, you make it, you multiply by -1, or if it is positive, make it negative. If it is negative, positive to get the conjugate. Okay? So you can use this formula here, guys. Again, if V here is actually V maximum divided by square root of 2. Same thing here. I is actually V maximum divided by square root of 2. Okay? When you do the conversion from time domain to the complex domain. If you want to do it, again, it's up to you. I'm totally fine. If you want to do it similar to what we did before, so the formula, and that's why in the textbook you will find the same formula, but it's actually V I asterisk divided by 2. They are the same. But here in this case, I'm going to only V maximum here, I maximum. When you do the conversion. So they are the same. Okay? This is for if you have a source. This is the power generated from a source. Now, what if you have an impedance? Z. This impedance can be only resistor, can be only inductor, can be only capacitor, can be combination, whatever it is. Okay? So here we have Z, we have current I, we have voltage drop here V. So how can we calculate the complex power here? We call it S, complex power. Okay? So the complex power here can be calculated by different ways. Number one, similar to what we did before, it can be V I asterisk, similar same thing as we did before. We have also it can be Z times I squared, the magnitude of I squared, okay, which is actually V I maximum, okay, divided by square root squared. That's why you can find this one in the textbook. Z I divided by 2. Okay, but anyway. Or it can be the third way you can do it. V squared, the magnitude of V squared divided by Z asterisk. You know what Z asterisk means? Okay. Whatever easier for you. So if I already have V and R, I can use this one. If I already have Z and R and I don't have V, okay, so it's easy for me to use this one. Yeah, yes, you can get V, but why I do it? If I can do it in one step, why I have to do it in 2 steps? Because I'm saying so you can use what if any one of them should give you the same result. Okay. Again, this one should be in the textbook. V squared divided by 2 Z squared. Again, they are the same because this one actually, when I calculate this one was V maximum divided by square root, but here is actually only V max. That's why they are the same. We will see now many examples. In this example, I'm going to teach using these formulas. We are going to use these formulas to calculate the complex, which is S. After you do the calculation of the complex power here, you will find S is actually equal to B plus GQ as I told you. Okay. Any questions? Yeah, maybe here I can tell you. If Z equal R plus GX, okay, so in this case, if I apply, for example, this formula here, if I apply this formula, so the power should equal R times I squared plus JX times I squared. So this is actually is going to be the active power because of the resistive load we have. And this part here is actually the reactance power because of the storage units we have. Again, guys, very important. It will be so sad for me if after you finish this course, you don't understand that power only consumed by resistive flows. Only the resistive flows can consume power. But capacitor or inductors, they don't consume power. They store and release. That's what I'm saying. So that's why we have here what we call reactance. Anyway, the next the next thing here I'm going to teach because the formula for the power factor. How can you calculate the power factor? I told you the power factor is actually for cosine theta v minus theta I. So the question is how I can get theta v and theta I? Yeah, number one, this is a very straightforward way. If you already have V, the voltage is actually V with angle theta V. And then I have I, which is equal to I with angle theta I. So if I already have the voltage and already have the current, okay, so in this case, I have this angle, I have this angle. So it's easy for me to calculate theta V minus theta I, and then it's easy for me to get the cosine after that. That's what we call power factor. There may be easier ways than this one. Okay, so if I don't, if I have like voltage here, and then I have here a load Z. Okay, if I know Z, okay, I can Z actually should equal to okay, the magnitude of Z with angle, the angle here theta V, theta Z should equal actually theta V minus theta I. So if I already have the loads, I have this load Z, so actually it's easier for me to simply get the angle of the load is actually theta V minus theta I. So I can take this angle, get the cosine of this angle, and this should be BF, power factor. So I'm explaining three different ways to calculate the power factor, and then you can use whatever is easier for you. If I already have, in the first example, if I already have V and I, so that means I have theta V and theta I, so I can easily calculate the power factor. Okay? If I don't have V and I, but I have Z, the Z here, so actually I can calculate the power factor from the angle here, because the angle is actually should be theta V minus theta I. Why? Why? Because actually Z should be V divided by I. And V is actually V with angle theta V, and I is actually I with angle theta I. So if you see the angle, it will be theta V minus theta I. So if I have Z, I can easily calculate the power factor. The next thing here also, what if I don't have Z, I don't have V, I don't have I, but actually I know the power consumed here. I know the power consumed equal to S with angle, with the angle here for the power should be theta V minus theta I as well. Okay, so this is the third way. So now what I'm saying, guys, to make it easy to calculate the power factor, you have three ways. You can select the easiest way for you. Number one, V is given to you know V and you know I. Okay, that means I know theta V and theta I. I can just subtract. This is number one. Number two, I know Z. Once you know Z, that means the angle here is actually theta V minus theta I. You can just take it and get the cosine. That's it. If you don't have Z and you don't have V and you are I and you have the power consumed here, the power consumed actually is actually the angle of the power consumed is actually theta V minus theta I. You know why? I'm gonna tell you why. Simply because, as I told you, this power is actually V times I asterisk, which is actually V with angle theta V times I with angle minus theta I. Minus because it is asterisk. So if you do the calculation, it will be V times I times theta V minus theta I. Makes sense? So this is the third way. It depends on which values are available for you. Any questions? Okay. Before we go to examples, so now we have everything we need for the example, except only one thing. I'm going to explain it now. We still here, even in AC circuit, we have the conservation of power. Conservation of power, which means the complex or active or reactive or average, any kind of this power generated would equal to complex or active or reactive or average power consumed. Okay. Maybe I need to be careful about the word consumed here. I mean here, this is This is the average power. I mean, generated here, I mean by the sources you have. So this is the power by the source, and this is the power by the impedance you have. But this is similar to what we did before. For example, if I have a source this way, and then you have resistance, and then you have your inductors, capacitor, whatever. So here, the total, the power here, plus the power here, plus the power here, should equal to the power here, generated here. Okay? So maybe I have to be careful with the word consumed here, because you know, inductor and capacitor don't consume, but they generate the active power. So I mean, the total power for the elements you have should equal to the total power generated by the sources. If you have more than one source, you need to add the total power of sources is a complex active reactive. Any question? I think that's all. This is the most difficult part. If you understand what I explain, now if you go to examples, everything will be easier. Okay? So here, yeah, that's what I explained. The two types of power we have. Okay. Let's see the first example here. I think I didn't teach it last time, but I think so. But let's see. In this example, I give you the current. This is I give you the current here. Is that right? Let's see. And then I give you the voltage of each element. I give you the voltage here. I give you the voltage here as well. And you know the current. So I know the current is given to me. And I have VS. I have voltage here, voltage here, voltage here. Okay. And then here I'm asking you to give me the average power. I want to calculate the average power of each element. So what is the average power here? Okay. The average power is this part here, which is actually V times I, okay, times cosine theta V minus theta I. Okay. You can use this formula if this one is V maximum divided by square root of 2. But you will find now in the textbook, here you put V maximum, and this one I maximum, now you have to divide by 2. Okay. And that's what I did. So as you see here, I got, for the first one here, I got V maximum, I got I maximum, okay? And then this one is milliamperes, that's why it's 0.721 divided by 2 times cosine. So now I need to find theta V minus theta I. This is theta, which is minus 15. Theta I is minus 41. This one. So this is the average power generated by the source, average power, okay? Now, let's do the same thing for the resistance. I want to find the average power consumed by the resistance. It will be the same thing as I did here. So what you have to do is same thing. What is the voltage here? I give you the voltage here, which is 18, as you see here. This is the maximum divided by 2. And then I'm going to multiply by the current. And then look at the angle. This is here. Theta V is here. Okay. And theta I is here. You can find the angle is 0. It's not a surprise. It's not a surprise. Almost in resistance, because the power factor is 0. That's why it's not a surprise to find that this angle is 0. Is that okay? Then I found this is the average power here. So this is the average power generated by the source. This is the average power consumed by the resistance. Do I need to calculate this one? For yeah, no, I don't need to. If you want to calculate it, but it will be 0. Because the average power for inductor capacity, average, not complex. Okay? It's only about average power. Okay, so the average power here would be 0, and now you can apply the power conservation. Okay, you can see here the amount, the average power generated by the source 6.5. The average power consumed by the resistance is also 6.5, and the average power consumed by the inductor. Yeah, if you wanna calculate it, you can calculate it, but you will find it is 0 if you calculate it, and it's not a surprise. I already know the average power. There are some things you already, even if you make mistakes in exam, you can correct yourself. Number one, is the angle here not 0, if it is a resistance, if the average power here is not 0, something is wrong. Okay, same thing here in this example, I use inductor. The same thing if it is a capacitor. Okay? Yeah, I forgot to tell you about this one here. After you calculate the complex power, okay, the magnitude of the complex power, we call it apparent power. Okay, so you know, complex power, it has two parts. P, this is the complex power, P plus GQ. The magnitude of this one, which is square root of P squared plus U squared, we call it apparent. Okay. So, which is actually this part here, which is V times I. So this magnitude is called apparent. Anyway, also I told you last time, because now we have different types of power, we need to differentiate between them. So as you see here, we are gonna use watt or kilowatt or megawatt for the active power. For the active power, I'm gonna use var, VCR, okay, or kilovar or millivar. Just check between them. This one is voltage ampere. This one is also voltage ampere.
What is actually voltage ampere? So I'm not using different units.
All of them are voltage ampere, but I use just different names to differentiate between them. And the magnitude of the complex power, which is called apparent power, we call it VC. Now, this is related to what when I told you here. I have some figures. Just see, I'm going to repeat what I said here, so you can see if you have only a resistance, and you have R and if you have I and V. So this is V, and the pink color here is actually I. Power is V times I. If you multiply V times I, you can find the red here. The red is the power, instantaneous power. You can see, and that's what I told you. You can see the power here is only active power. It's always positive, active power. But in case of inductor, you can notice here, this is the power in blue. As you see, this is the power here. It's reactive power, okay? It's reactive. Same thing, if it is a capacitor, it's also reactive power, as you see here. Okay? I didn't do anything. I just multiplied. I multiplied V times R. Yeah, then I found this is the power. We already know that in case of a capacitor, we have only the active power. Okay? And in case of resistance, we have only active power. Okay? But there is something important here, and it's related to when I told you we have something we call it power factor correction. So that means at home, if the power factor is far from 1, I have to add inductor or capacitor to bring it back to 1 to reduce losses. Okay, to reduce the so that's what we, to reduce the reactive power, and that's what we call it correction. Okay, there is something interesting here. I will show you. So if you look at so if this is if you have only a resistance, this is the power. The red. Look at the red here. The red here is actually the power of the resistor, okay, which is active power. But if you look at the power, of inductor and capacitor, you will see both of them are reactive power, but they have opposite direction. Okay, so when this one is positive, this one is negative. When this one is negative, this one is positive. You can see here. And here comes the idea of power factor correction. Okay, that means, for example, here at the load, I can try to add some inductance or capacitor so that they cancel each other. When this one release, it can release here. This one can release here, and so on. Okay, so this is the main point, or this is the idea of power factor correction. Because luckily, when one of them is positive, the other one is negative. That means this power can come, this one can inject in here. Okay, so the power can be always between this one and this one, and we avoid. This should happen when the power factor is 1. Okay. Let's see what more examples. So in this example, I have here a resistance I have R in parallel to L. Here I give you the total I, I here. I give you this I here, this current I. given here. Also, here I give you R and L. I give you R and L. And then I ask you, what is the value of complex power delivered by the source? So I want to know what is the power delivered by the source. Okay, I give you several formulas. You can use the easy formula. The formula. It looks like for any formula you need to get the total Z, the total resistance here. Sorry, total impedance. So the total impedance here is actually R in parallel to L. So I got Z. Is that okay? Once you get Z, now there is a you can calculate V. Why? Because V, the voltage drop here should equal I times Z. This I is gonna go through Z. Okay, you can get V. Once you have I is given to you and you have V, you can calculate the complex power this way. Divided by 2. The textbook can divide by 2 because this is the maximum, I max. Okay, so now you can get the maximum. Okay? So if you go to the formula I explain, if you have I and you have Z, actually you don't need to get V. Okay, but this is one way you can do this way, or there is another formula I explained here, which is, yeah, maybe this one is easy, right? So, and when you go to you find both of them to be the same solution. Okay? Because I have I, it's enough. I can just use it. Okay? I don't need to calculate B, and then after get B, you multiply this. This one is easy. And you have I, you can just using this one. You get the same. So this is the complex power I have. This is the complex. And the complex power is in unit. The unit is VA, voltage ampere. Now, the next question here, I need to, next question, what are the values? Now, I want to change R and L. So in the first part of the question, I give you R and L. Now, I want to change R and L. What is the new value for R and what is the new value for L if I want to deliver this amount of power? This amount of power is different from what we have here. Okay, so given the same current I have, okay, I want to change R and L so that the delivered power will be this amount. So I give you the power, you have the power, you don't know the impedance, you don't know R and L, you know the current. Okay, always you try to think what you know and what you don't know. Okay, so now I know the power, this is the complex power, I know R, okay, but I don't know the impedance here, the impedance I have. For sure, this should be easy. When if you go to the formulas I have here, you can use you can use this formula, right? So you have S, and then you need Z. I don't know Z, okay? And you know R. This is the easiest way to do it. The easiest way you can do it is actually you can use this one here, this in order to get Z. Okay, this is the easiest way. There is a more difficult way, which is this is the one they used in this example. Is actually I know S and I know R, so I can get V. I get V. Once you get V and you already have I can get Z because Z should equal V divided by R. Both are okay. So whatever easy for you. Okay? So here you can see in this example. Yeah, I think the way it's calculated, as I told you here, this is a complex power. It's given to me. I is given to me. V is not given. So by this way, I can get V. Okay? Once you get V and you have I, now you can calculate Z. Okay? You need to do 2 steps. It may not be the easiest way. The easiest way, as I told you, you can do only in 1 step. Okay. So now, once I get Z this way. So this is the total resistance. Okay. So actually here, I'm gonna get, so how, if I give you Z this way, how can you find R and you find L? This is the total resistance. So what you have to do is, or because they are in parallel, okay, let me explain it here. For example, if they are in series, for example, if you have something like this, if they are in series, and then when I calculate the total resistance, for the total Z, I found the total Z, for example, equal 3 plus G5. Okay? Very easy. So that means this 3 is here, this is 3, and G5 is here. Very easy. Then what I did here, I did the opposite. So if I know this one is 3 and I know this one is J5, so how can you get Z? Z should equal to 3 plus J5. Now it's the same thing when you do the opposite. Okay. But now it's a little bit difficult because it is in parallel, not series. And I'm gonna make it easy. I'm gonna tell you how. When it is in parallel, okay. So actually here, Z should equal to R in parallel to X. This is R and this is X. Okay. So which is actually R times X divided by R plus X. But I'm not gonna do it this way because this way will be difficult. Okay, but I'm gonna do it in an easier way. Okay. So now, you know, if I look from here, I can say Y, you know why? Y is actually 1 over Z. Okay? Admittance, like conductance, 1 over R should equal to 1 over R plus 1 over X. And this one should equal to 1 over Z. Okay? So this is an easy way. So what I can do now, guys, is I have Z, I can calculate Y, which is 1 over Z, and this one should actually, this one should have a real part. The real part of this one will be 1 over R. The complex part will be 1 over X. I think this will be easy. I think that's what we did in the example here. Yeah. So here, I got here 1 over Z, this part here. 1 over Z, it has 2 parts, as you see here. The first part here is 1 over R. So 1 over R. So I need to flip this one. 1 over this value should equal 30 ohms. And then this one here, it has to be negative. Remember, if J is positive, so this is L, right? Inductance. If it is negative, so this is the capacitor. But this is not the impedance. This is 1 over the impedance. That's why 1 over the impedance in case of inductor has to be negative. Okay? So that if I take this part, 1 over this part, it's going to give the impedance. Okay? The impedance, which is J omega L. So now because I have omega, so I already have omega L, so now I can get L because I know omega, right? So X is actually equal for omega L. Omega is given to me, now you can get L. Any question? Let's have more examples here. Let's look at this example here, guys. I have again, it's not difficult. It looks difficult, but it's not. Just like some formulas, if you understand the formulas I explained at the beginning of this lecture, and then for any question, you need to know what I have, what is missing, and then you use the formula for that. That's it. It's easy. So let's see here, for example, here. In this example here, we're assuming we have here, we have 2 loads. One we call it A, and one is we call it B, and we have a voltage source here. Let's see what is given to me and what's not given. Okay, and again, you need to know what's given, okay, and what formula you have, and which formula you have to use to find the missing parameters here. Okay, so it gives me the voltage. I know the voltage here. I know the power here. So SCA, I know the power of A, given to me the power. Here, I know the impedance of this one. It's not power, but I don't know that's all what I need. I know. So here, for this one, I know the voltage because they are in parallel. So the voltage here should equal to the voltage here, equal to the voltage here. So for this element, I know the impedance and also I know the voltage. For this one, I know the voltage and I know the power given to me. And now for this one, I know the voltage. So let's see what is required here. Number 1, determine the value of the complex power delivered by the source to the parallel load. I want to know what is the total power delivered to the load here. Okay. You can solve it in different ways. Okay. Let's see how can you do it. Okay. In order, I know the voltage here, so I need to find the current. I know the voltage. I need to find the current. Okay, this is one way. It may not be the easiest way, but this is one way. Okay. I will solve it in different ways using the formulas I explained. So one thing here, I know the voltage and I need the current. The current here equal to this current plus this current. Okay. Can you get the power here? Okay, sorry, can you get the current here? Yes, I can. Why? Because I know S and I know V. If you have, and S is equal to V times R. Okay. So by here, I can easily get I can get the current here. S is given to me E is given to me, I can calculate I. Okay, so I can find the current here. Okay? Here, for this one, I know the voltage, this one. Also, I know the impedance here. Can I get the current here? Yes. You just divide the voltage by the impedance, and that's what I did. Okay? If I know the current here and the current here, and you apply Kirchhoff current law, so the total current equals the summation of two currents. That's what I did. I get the first current, the second current,
added
the
the
two currents together, I got the total current. That's okay? Once
If
I
I
get
get
the
the
total
total
current,
current,
I can calculate the power. The power is V, and the total power I have. This is the power of the source we have.
when we
In my opinion, maybe we have an easier way. We don't know the easier ways. To me, the easiest way is, instead of making many steps this way, I'm going to tell you now. Okay, look here. Because there is power conservation. Because there is power conservation. That means the power generated here equal to the power here plus the power here. Power here, this power here should equal the power here plus the power here. This power is given to me. SA is given to me. So that means if I can find the power here and I add these two powers together, I can get the total power of the voltage source. Okay. But how can you get the power here? You can, because you know V and you know Z. And there is a formula. I'm gonna go back to here. There is a formula here. If you know V and you know Z, if you know V and Z, you can easily calculate the power. Only one step. You just calculate the power. You have the power of the second branches, and then add them together, which is equal to the power of the source. This is power. For sure, you can try to solve it in any other way. Okay? Okay, now let's come to the second question. Second question, we want to find the equivalent of the total impedance of the parallel load. Okay. Okay, what's the problem now? The problem now is that to solve this one, I already have the impedance of, but I don't know the impedance of A. Make sense? So I know this, I need to find the impedance of A, and then they are in parallel to each other. I have B is given to me, but A is not given. Okay? But for A, I have the power, and I have the voltage. And I need to find the impedance of A, given the power and given the voltage. Can you do that? Yes. You have only one formula to do that. If you go back to here, I can use this formula. You have the voltage, you have the power, and I want to find Z. Okay? But you need to be careful. Z, what I'm going to calculate here is this sum. This sum. Okay? That means after you calculate Z, when you get this star, in order to get Z, okay, you have to multiply the angle by -1. Or if it is in a rectangular form, the term multiplied by J, you have to multiply it by -1. Okay, guys? I don't know how he solved it. Yeah. He solved it in a different way. The way the textbook solved it is actually, and why you can practice when you go home, try to solve it. You have the recorded video. I explain you can do things by different ways. When you go home, you can try to do the other ways and compare the results. It should be the same numbers you will get here. I did it by myself. Okay. So here, other way here, if I know the current here, and I know the voltage, I can divide voltage by current. Because in the previous step, I already calculated the current here, and I know the voltage, I can easily get the impedance. Any questions? Let's have one more example here. In this example, verify that complex power is conserved. What means the complex power is reserved? It means that means the power generated by the source should equal to the power here plus the power here plus the power here. The total power. Okay? So now this is the meaning of this conserved. So the power generated here will equal to the total power we have here. Okay? So anyway, so let's see. Here I give you V is given to me. So I give you V. Okay? So you can calculate the total resistance total resistance here is actually R plus J omega L plus 1 over J omega C or minus J1 over omega C. Okay. So now I have the voltage. I can calculate the total power this way, and by this way I can calculate the current. This current in series. Okay. So now once you have here the current, you can actually calculate the voltage of each one. That's what I did here. So once I know the current, I can multiply this current by R to calculate VR, calculate the current by L to calculate J omega L, sorry, to calculate VL, the voltage. So I can get the voltage drop on each one. Again, you don't need to do that by way. If you want to calculate the power here, if you know the current and you know the impedance, you can calculate the power without the need to calculate the voltage. Okay? Because I already have a formula. I have a formula here. So if you have the current, you have the impedance of each element, so easily I can calculate the power. But anyway, so here's the way it was solved here. I know the current, I know the impedance of each element, so easily I can calculate the voltage drop in each one. Okay. So now I know the voltage here, I know the current, voltage, current voltage. So now I'm gonna calculate the power of each one. Okay, because I know here for each element here, I have the voltage and the current. Okay, so by doing that, now I'm gonna calculate. This is the power of the source. This is the power of the resistance R. Okay, it's not a surprise that I find the angle is 0. It's not surprise. Okay, now this is the angle. This is the power of L. Okay, and always if it is only inductor, the angle has to be 90 all the time because there is a 90 difference between current. If it is only inductor, okay. Here also, if it is only capacitor, it should be negative 90. Anyway, and then, so this is the power generated by the source. This is the power consumed to the power of each element. I can add them together. After I added them together, I found equal. They are equal. Okay. We have the same thing in DC circuit. We go back. Okay. In DC circuit, the power consumed by the sources. Okay, should equal to the power consumed by, generated by the sources should equal to the power consumed by the resistor. Any questions? Here I'm explaining the idea of the power factor as I told you, and I give you several formulas to calculate the power factor. But there is a small thing here I want to explain. I did not explain the power. I explained how can you calculate the power factor. Let me do here because I want to add a small thing here. Yeah. Yeah. I told you guys, if you want to calculate the power factor, okay, it has to be cosine theta V minus theta I. So the first case here, if you have V and I, that means you have theta V and theta I. So it's easy. You can just take these two here and calculate the cosine, the power factor. The other possibility, if you have Z, if you already have Z, so the angle of Z, okay, this is actually theta V minus theta I, so I can take it and get the cosine. The other possibility, if I know the power here, if I know the complex power here, the angle of the complex power is actually theta V minus theta I. So whatever available, whatever easy for you, we have three ways to find theta V minus theta I. Once you have theta V minus theta I, you can put it in the cosine. Is that okay, guys? But there is a small problem here. Is that enough to tell you if the power factor equal to 0.7 or 0.8? Is this enough? Is that enough? It's not enough. You know why? Because cosine, because this is the result of the cosine. Cosine is actually an even function. That means if you cosine 30 or cosine negative 30, that means if theta V greater than theta I or theta I greater than theta V, in both cases, I will have the same value for power factor. That I'm saying. So this information, when I tell you the power factor is 0.7 I, okay, I can know You can know theta v for sure minus theta I. You can calculate it, okay? But you don't know if it is positive or negative. Because in both cases, if v is greater than r or I is greater than v, in both cases, cosine will make it positive. You understand what I'm saying? That is why when I give you the power factor, I should not just give you a value. I have to tell you if this value is leading or lagging. I have to give you another information, okay? If C is if theta v minus theta I greater than 0, positive, if this one is positive, okay? That means theta v is greater than theta I, okay? It is positive. In this case, I'm gonna tell you it is lagging. Okay? It is lagging. Okay? Because lagging means I, because theta v is greater than theta I. So lagging means I is lagging v. Because I, theta I is small, smaller than theta v. So that's why lagging. But if theta v minus theta I less than 0, that means it is negative. If the angle is negative. Okay? Again, once you take the cosine, you will not see the difference because cosine, if the input of the cosine positive or negative, the result is positive. This is a problem. That's why I have to tell you here in this case, I'm going to call it leading. So when you see leading, that means theta I is greater than theta v because I is leading. If I tell you this is lagging, that means theta v is greater than theta I. That I'm saying. So again, when you calculate the power factor, it is not enough to just, when you get theta v minus theta I, yes, you need to find it. You need to calculate the cosine, and then you get the result. If the result, for example, 0.6, it's not enough to say the power factor is 0.6. It's not enough. You have to tell me it is 0.6 and it is leading or lagging. Leading or lagging, it's related to the current. Current is leading greater. The angle of the current is greater than leading. In case of leading, that means this angle is greater than V. In case of lagging, so the current is lagging or the current is leading. So we always get current. You understand what I'm saying? Is that okay? Yeah. So let's have more examples here. Yeah, maybe I'm gonna go to this example first, and then I will come to this one. So let's have this example here. It's just a very easy example. Look here, guys. In this example, you have a voltage source here, and then you have RLC, as you see here. Okay. Again, because they are in parallel, so the voltage here should equal the voltage here, equals the voltage here, equals the voltage source here, as you see here. I give you R, I give you L, I give you C. All of them are given to you. Okay. Here I'm asking you, find the complex, active, reactive, and apparent power of each element. By the way, this only one requirement, because if I can get the complex, it's easy to calculate the active, because the active is the real part of the complex. It's easy to calculate the reactive because this one is the complex part of the complex power. Apparent is actually the magnitude of the complex. Okay. Anyway, so for each element here, for this one and this one and this one and this one, for each element, I want to find the power for each one. Okay. First of all, as you see here, you need to convert the circuit from the time domain to the complex domain. R will be the same R, L will be J omega L, C should equal to 1 over J omega C. Okay, when you do that. The difference between this chapter and what we did before, when you convert the source here, it has to be, you are not going to make the magnitude 20, but it has to be 20 divided by square root of 2. Only for the voltage. Okay? So it's going to be 20 divided by square root of 2. If you want to use the formulas we have here in this chapter. Okay. Anyway, so once I do that, as you see here, once I do that, by the way, there will be an exam, one question in the final exams here. It's going to be very easy. It's going to be something very close to this. It's not going to be complicated. If you know the formula I explained, it's going to be straightforward application with the formulas I explained. Okay. So maybe it's going to be very close to this example somehow. Not identical, but if you understand it, you can just apply it. Okay. Now I want to calculate the power here. What is the power here? You already know the. So for each one of them, look here, guys. For each one of them here, I know the resistance or impedance, and I know the voltage. Yeah, there is a very easy formula for each one of them. This may be the easiest way to do it. The easiest way here to do it, if you know the voltage and you know the impedance, you can calculate the power directly. You don't need to calculate the current, and then after you calculate the current, you use the first formula here. You don't need to do that. You can just use it directly. Okay. Same thing here. If I want to calculate for this one here, I need to know. One way to do it is I can get the total impedance. Total impedance is one way to do it. And then once you have voltage and total impedance, you can calculate the power of this source. Or you need to find the total current. Once you have the total current V, you can do it as well. Let's see how we solve it here. Let's start with the resistor, with this resistor. That's what I told you. It's going to be V square, the magnitude of V square, divide the voltage here, the magnitude of this voltage here, okay, which is actually V maximum divided by square root of 2, okay, divided by the resistance asterisk. You know, because here we don't have imaginary part. The asterisk of 20 is still 20. 20 of a real number, it's still the same thing, real number. Anyway, so after I calculate the resistance here, I can find it is 10 plus G0. It doesn't have imaginary part. It's not a surprise because always for the resistance, we have only active. We don't have imaginary part. Okay? So if I ask you, what is the active power? This is 10. What is the reactive power? This is 0. Okay. And now, what is the magnitude? That's what we call the magnitude here, which is square root of 10 squared plus 0 squared, which is actually 10. Okay. Any question for this one? Okay. For every element, I will repeat it for each element. I can repeat it for each element. Okay. But instead, but I'm gonna, because all of them have the same voltage, so this part will be the same for all of them. But for the resistance, here we have different resistance here, as you will see. Okay, so here if I come, or sorry, impedance. If I come to this one here, I'm gonna repeat everything. We have V squared, but here I have to use the impedance of L. Okay, this is ZL. ZL is G15, but because of this, because we need to calculate the conjugate, it has to be negative G15. And now, after you calculate the power, you can see here, the active part is 0. It's not a surprise for inductor and capacitor to find the active part is 0. It's not a surprise. This is how it is. What I'm saying? If it is pure inductor, pure, there is no resistance. For sure, if there is a resistance in series or in parallel, this will be another situation. Here, we're talking about it's only pure inductor. Okay? It's not a surprise if it is 0 here, and we have only imaginary part. So now the active power is 0, the reactive power is equal to this value, and this is the apparent. Same thing when you go to the capacitor, I will repeat everything again, but this time I'm going to use the impedance of the capacitor. Okay, again, it's not a surprise that the active power is 0. This is because here we have active power of 0, but we have here the active power. This is the reactive power we have. Okay, guys. Okay. Second question, I wanna find the total impedance. Total impedance. If you look here, yes, for sure I will explain how can you get the power of V. I found the power R of Z, and so I found the power here, but I didn't calculate this part. This will be the next question. But now I want to find the total impedance as seen by the source. So the total impedance here is R in parallel to ZL in parallel to ZC. So after you calculate it, I find it this way. This is the total impedance. Right? If I ask you, what is the power factor here? If you can calculate the power factor, what is the power factor? Here, one of the things to calculate the power factor is, this is the easiest way. If you have Z, so actually the angle of Z is actually theta V minus theta I. It's given to you. So all what you have to do is This angle here is theta b minus theta r. So all what I have to do, I have to take the cosine of this, whatever the value is. This will be the power factor. Is that enough? No, I have to say it is leading or lagging. Okay. Theta b minus theta I is negative. What it means? Means I is greater than V. And because I is greater than V, so I is leading. So this should be leading. Okay. I told you when it is negative, it has to be, it means it is leading. Leading means the angle of I is greater than the angle of V. So now, if you want to calculate this correctly, you have to do one thing. You have to the value of the power, and you have to it is leading or always it is negative, it is leading. Okay. Okay. Now let's come to the last part. I want to calculate the power here of the source V here. Okay, guys. You can you can calculate it in three different ways. The first way you can calculate it, I already calculated the power of R and the power here and the power here. And because there is a power conservation, there is power conservation. That means the power generated by the source should equal the power here plus the power here plus the power here. Make sense? So this is the first way you can solve it. So here I'm going to show you how can you solve it in different ways. The first way, because I already know the power here, the power here, the power here, I can add them together, and this should equal to the power generated from the source, power conservation. And this is the first way I did it, okay? There is another way I can do it, which is I already know V, and I already know Z, the total Z. You have V and you have Z. Can you calculate the power? Yes, I can use this formula here. V squared divided by Z. Or I have V, I need to find R. Once you find R, so the power is going to be V I asterisk. V I asterisk. Okay? By the way, this one is the power of the total impedance Z, which is equal to V because they have the same power. The power generated by the source should equal to the power generated by the loop Z. Okay? But anyway, another way, I already know V. I already know the total resistance, impedance. I can find I. Once you have I and you can find V, you can use it this way. Any question? In the three cases, you will find it's the same. Power is the same. All right. Again, the most difficult or the most important part here in this is actually what I explained. Again, I will post the video if you missed the first part in the lecture, okay? Because actually here in the first part of the lecture, I summarized everything. We have several formulas here. That's it. Everything is just very straightforward application to these formulas, okay? When I post, if you missed something here, I will post the video. You can go to the video again and you need to write this formula and memorize it, okay? Let's see one more example here. We still have time. So let's see one more example here, guys. In this example here, I'm telling you we have like a consumer plant has two parallel loads. So here we're assuming we have two parallel loads here, and it gives me some information. And for the wire, for the connection, it makes a source. This is the source we have, like power plant, and it's like a transmission line. For the transmission line, we have a resistance, we have inductor. This is the load. This is my load. We assume we have two loads. One load. Well, this. But first of all, this kind of question, you need to understand what is given to you. Okay? And then you need to understand what formula I have to use to find the missing part or the part you need to solve. So here I give you what is given to me here. I give you the voltage here. The voltage here is VRMS is 10 kilovolt. This is the voltage in the load. We have two different loads here. We have one load, okay, which is 50 kilowatt, and power factor is 1. When you see power factor is 1, what it means? It means this load is resistive, only resistance. And actually it's mentioned here. So let's see. The first load consists of 50 kilowatt of heating, and it is resistive. That's why power factor is 1. So here, slide. Here I have a heater. We are using the heater, and this heater is just a resistive load. That's why the power factor of this load is 1. The second load is a motor. Motor has a lot of inductors. Motors have a lot of inductors, okay? So that's why for the second one here, the second load is a set of motors that operate the lagging power factors, 0.86 lagging, and it gives you the magnitude of the power. Okay? Anyway, what do you want me to solve? So you need to find, I need to find the total current flow from the utility line into the plant, okay? And the plant is overall power factor. So I need to find the current, okay? So if you see here, guys, I give you the voltage. You have the voltage here, okay? VRMS. So now I want to find the total current here, okay? Let's see how can you find it, okay? I have the first power. What is the power here? What is the complex power for the first one? It's just 50, because this is a resistance. It does not have an imaginary part. So for the first load, the complex power is just 50 kilowatt, because the power factor is 1. Okay, because this is a resistance. It doesn't have an imaginary part. Okay, what is the complex power here? The complex power here has a magnitude which is given to me, and it has an angle. This angle is actually you can get it from the power factor. If you go to the formula I give to you here, I told you here in this formula, if I give you the power, the angle of the power here is actually theta b minus I. So if I give you the power factor, you can actually calculate theta b minus theta I from the power factor. Okay? So now I give you the magnitude. Now I can get the angle, but you have to be careful, because power factor is a design. It's always positive. Okay? So what you are going to calculate from this design, always this. Now, that's why I told you leading or lagging. So whatever you will get, it's going to be positive, or you need to add negative. Okay? If it is leading, okay, so you need to add has to be negative. Anyway, so let's see how. So now I calculated, I know the power factor, I got the inverse of cosine, I found it is 30. And because it is lagging, it's going to be positive. I'm going to keep it positive. But if it is leading, I'm going to make it negative. So now I have the two power. I have the power here, and I have the power here. Okay. If I add them together, if I add these two power together, I will get the total. I will get the total power. Okay. So you can see this power has only a real part. Okay. But this power here, it actually has a real part, but also it has an imaginary part. Okay, it has two parts. Okay? So now I can add the two power together. This will give you the total power. Okay, guys. So now I have the total power here, and I have VRMS, the total power and VRMS. So what you want me to solve here, I need to find the current. So the current is actually after I get the total power. Okay, this is the total power. From the total power here, I can get this is the real part for the total. This is the total power is here. I can get the magnitude of the total power, which is actually V times I, okay, or Vm divided by square root Im divided by square root. This is the real part. Sorry, this is the magnitude, because I have VRMS. I can get RMS easily. Again, after I calculate the total power, can you calculate the current given the voltage? Yes, because the magnitude here, the magnitude of the power should equal to the magnitude of I times magnitude of V. Okay, that's how it is. So let me come here. Yeah. Here you have power is equal to V times I active. This one should equal to V with angle theta V times I, okay, with angle minus theta I, minus because this asterisk here. So this should equal V times I times theta V minus theta I. Okay, that's what I did. I have the total power, so I can say the total, this part here is actually the magnitude of this. And the angle now is theta V minus theta I. So now I can get the new power factor. Yeah? So you will see now. So again, after I calculated the total power, this is a total power. From the total power, I can get the magnitude here, put it here. So the magnitude, okay, when I divide, the magnitude here should equal V times I. From here, I can get I, okay? But also, if you look at the angle here, this is the angle is theta V minus theta I. Okay? So if I get the angle here and get the cosine, now I'm going to get the power factor. Okay? And the power factor should be cosine of this value 0.94, and it has to be lagging because it's positive. All the time when the angle here is positive, it has to be lagging. Negative, it is leading. Okay, maybe there's something that should confuse you. Listen to me. This is the power factor for this load alone. If you have this load alone, if I have this impedance alone, this load alone, I have a power factor of 1. Make sense? But now, if I have this one alone, I have a power factor of 4.66.
This one alone. But for both of them, if I have the two rows together, what is the power factor?
Okay. This one was 1. This one is 0.86. Now the power factor is 0.94. For both of them. Okay. So again, you can see when I change the law, very important thing, I'm going to build on it next time. Please just give me 1 minute. Okay, you can see here, guys. If I have 0.86,
I added something here, I changed the total power factor.
see? And this is what next time you will see. If I have here, you will see now, in the very beginning, this is my load here, R and L. And have a certain power factor. And I want to improve the power factor. You will see, I will change the load by adding the capacitor this way. The purpose of this capacitor is just to improve. And that's exactly what we did here. You notice something related to what I explained. That's why I want you to understand, because that's what I'm going to build on it next time. So you can see here, you have only one load, okay, and this one alone, this one alone. But when I put both of them together, okay, if the power factor is not good, I can add a capacitor, I add a resistance so that I can increase the power factor. Very important. I think that's enough for today. I have the exam. We're going to study the exam.